Perfect, thanks. So just to start off, as an important act of reconciliation and gratitude, I do want to take a moment to acknowledge that I'm joining you today from Treaty 6 territory, the traditional homeland of Métis and Inuit and the ancestral territory of many First Nations, including the Cree, Dene, Blackfoot, Saulteaux, and Nakota Sioux. We acknowledge the many First Nations, Métis, and Inuit who have nurtured and cared for these lands since time immemorial. If you are joining us from elsewhere and you want to share an acknowledgement, please feel free to do so in the chat. So good afternoon, everyone. My name is Pamela Gertzen. I'm the Executive Director of the Smart, Sustainable, Resilient Infrastructure Association, which we shorten to SSRIA. So SSRIA is a not-for-profit organization that is really taking a collaborative, industry-led approach to accelerate the adoption of low carbon solutions in the built environment. We're currently funding 16 demonstration projects across Alberta and actively sharing those results through webinars like this one today, and then through our Building Innovation Reference Center, which is a searchable online database of information related to each of those projects and can include details from planning and design documents to energy models and final project results. So our next webinar will be held March 21st, and that one will be on micro CHP in a mixed-use building. You can look for details on that event in our next newsletter. And so if you are not already subscribed to a newsletter, I would recommend you do that, which you can do on our website. When I'm done and pass it off to Zhongyi, I'll also put a couple links into the chat, including that one. So the newsletter does share details on upcoming events, industry news, and opportunities. So lots of great information is shared there. We also just recently announced the dates for our big annual event, which is the Alberta Energy Efficiency and Innovation Summit. That is taking place June 20th and 21st, and will be fully in person here in Edmonton. Early bird registration is expected to be opening up in the next few weeks, probably early March. And we also have a range of sponsorship opportunities if that's of interest. So if you do have any further questions about that or just about SSRIA in general, certainly feel free to send me a direct message in the chat, or you can always email me. And I will also put my email address in the chat. So for today's webinar, we have Zhongyi Quan, the founder and CEO of SwiftCharge. So Zhongyi and SwiftCharge is working on a project with the U of A to demonstrate a building-friendly smart charging solution in a number of University of Alberta car parks. And so that project is well, it's more than just getting underway, but starting to collect some data. And so Zhongyi is here to give us some additional information about SwiftCharge and about that project. And so with that, I'll pass it off to Zhongyi.
Sounds great. Thank you, Pam. Let me just pull up my slides, share my screen. So can I see my screen? Yeah, perfect. So like Pam mentioned, we're SwiftCharge, and so what we do is we are developing a smart charging solution that can be deployed anywhere. So a little bit information about us. So like as mentioned, we're developing a smart charging solution, and the goal is to reduce the installation costs for EV chargers by 50 to 90%. And by doing that, we can deploy EV chargers at any locations so that we can build a widespread charging network across North America. So we have about 14 team members right now. John and I we're the two founders, and John was John is a former ethical employee, and so I did my PhD from the U of A, and all I done before was EV charging, and that's how I started with EV charging. And in addition to our team, we also have advisors. as you can see here. So as Pat mentioned, we're working on a pilot project with UFA right now, and we're deploying 20 EV chargers at two of UFA's car parks, Windsor car parks and Stadium Park car parks. Chargers. So now we have 3 chargers online at the Windsor car park. So we're doing testing using actual EVs right now. Yeah, if you pop up at the Windsor car park, first level on the south side of the car park, you see the 3 chargers online. We're also installing EV chargers at a number of other locations, including Nate, Fairmount, Holiday Inn, a few Holiday Inns, and other hotels, some customers in BC as well. So what we do is, we offer 3 products, I can say. So one is the software platform. We use that to manage and control the EV chargers. It's a cloud service. We use that, talk to the chargers from the cloud and get the information. And I'll introduce more about that later. So we have a level 2 chargers, which is a smaller box. Usually we use for condos and apartments, hotels, families, single family houses. And we're also developing our own fast charger, which is a very unique product. I won't talk about the fast charger today because our focus right now is to do the level 2 chargers with the UFA project. So with that, I'll just jump into the presentation. And right now, everyone's, I think there's no question about EV adoption now, because we've seen a clear trend that EV adoption is increasing rapidly. And we're looking at 120 million EVs on the road in North America by 2040. And so the main reasons behind that are people starting to know that EVs have a much lower life cycle carbon emissions compared to combustion engine cars. Many studies have shown that even with the current mix of the fossil fuel based power grid, EVs still have a very low life cycle carbon emission. And with more and more renewables penetration in the power grid, EVs will be much more clear than today in the future. And also, EV has to offer the benefits on the consumer side, because there's basically a very low maintenance cost or even zero maintenance cost. And it's very convenient to use because people now, they don't need to go to the gas stations anymore. They can just charge at home. But that only works for single family homes. It's still challenging to put in chargers at multi-family dwellings. I'll talk about that later. So before we jump into the problems and solutions, we just want to introduce introduce EV chargers in general. So we've seen different type of EV chargers. Generally, we have 3 type of EV chargers. So one is what we call level 1 charger, but we don't talk about that anymore today, because level 1 charger is just a wall plug to the wall. It's just a charger plugged into the wall plug, and power is very low. It can barely keep the battery warm. So if we want to use that to charge a car, we'll need 2 to 3 days to do a full charge, depending on the size of the vehicle. And therefore, basically, no one's using that today. And then there are level 2 chargers. So level 2 chargers, the power of level 2 chargers started between 3 kilowatt to 19 kilowatt. So you can do a full recharge of a regular EV in about 5 to 8 hours. And that's now a very popular solution for single family homes, and also for condos, apartments, workspace, hotels, where people don't need a very fast charge. You can just park the car there for several hours and wait, and just at home or at the office where the car is being charged. And there's also a fast charger, which is also known as level 3 charger. So the power of a fast charger is very high, usually, and we've seen that Tesla supercharging station. We've seen that in commercial locations where there's high traffic, and then fast charger can do a recharge in less than 30 minutes. And the two type of chargers require different infrastructures. The level 2 chargers generally use a lower voltage, 208 volts or 240 volts, because the power is low, so they use lower voltage. But the level 3 chargers, they usually use a higher voltage, 480 volt or 600 volt in Canada, because the power is very high. And with a higher voltage, we keep the current low. And the two types of chargers have different impacts on the grid as well. So for level 2 chargers, because one charger only draws 3 to 19 kilowatts, so it's not really a lot of power. But if we have a large car park where we need many level 2 chargers, it can be a problem for the power grid infrastructure. But for level 3 charger, a single level 3 charger can draw 100, sometimes even 300 kilowatt power. And then for a single fast charger, a single level 3 charger can be a challenge for the grid infrastructure. So what we've been talking about a lot about is the electrical infrastructure or grid infrastructure. So we've also seen the news about how EV charging will affect the grid infrastructure. And here's the case study published by California Energy Commission to clearly show the problem. So we can see from this picture is like a map of California, but the red lines here are the areas, show the areas where the grid infrastructure just cannot support any additional EV charging without any thermal or voltage violations. You can see those locations, well, the available power capacity is already negative. So a single EV charger can just cause a big problem for the power grid. And even for a lot of other locations, the available power is not enough as well. And this is a case study in California, but it's also a problem, a very common problem for most jurisdictions in North America. For example, in Alberta, we have the same problem, and also in BC, Ontario, basically anywhere. And if you further look at this and compare this map with the population density map in California, we see that the grid infrastructure is the available capacity is negative at locations where people live. Most people live. So that means for locations where chargers are needed the most, we don't have the infrastructure to support EV chargers. And even for locations where not many people live there, like the highways or tourism locations, we don't have the power grid to support EV charging either. So that's why a lot of times we have seen that the grid infrastructure is the bottleneck for electrification. So well, that's on a higher level. It's the grid is the bottleneck for electrification, but at Swift Charge, what we're trying to do is we focus on one problem, is for multi-unit residential buildings or commercial buildings with large car parks, like office buildings. On a smaller scale, the problem will be even clearer, not just about power, it's also about the cost and also about emissions, a lot of different things. And also, why do we need EV chargers at those locations? It's because more and more people will live at MURBs, condos, and apartments. People will work at high-rise buildings, for example, downtown. But those buildings, they don't have a very large power distribution capacity to support EV charging. And this is a forecast by NRCan. We see that in Canada, we anticipate at least 30% of residents in condos and apartments will need to have access to EV charging, and that's a very conservative estimation. And the real case right now we have seen is they're actually on track to 100% EV penetration in condos and apartments. So eventually we will need at least 50%. For some buildings, we will need 100% EV charging access at those buildings. But that is not possible today because of the power requirements. for EV charging. So why is that a problem? Let's just look at the a typical level 2 EV charging infrastructure. So this is very common for like different locations. It's just a typical electrical structure. So we will have a transformer from the power grid. Transformer can be in the electrical room, and then after that we have the panels, and there will be breakers inside the panels, and each breaker support an EV charger. So we can have multiple panels. We can also have a main transformer and several transformers. But overall, that's the system structure. So anything before the EV chargers are electrical infrastructure. And based on the electrical code, we need to make sure that the size of the transformer and also the size of the panel are well designed so that the chargers won't overload the panel. And and because of that, the size of the infrastructure is directly related to the size of the EV chargers. And still for the let's just look at the condo case, and this is the project we're trying to get to deal with. It's a condo with 200 parking spots, and the owner, like the building owner, the developer wants to have at least the 50% coverage for their EV chargers, of the parking spots for EV charging. So if you look at this, that means over 100 EV chargers, and each EV charger can draw like a 32 amp. It's a very like a low speed level 2 charger, and each charger will have like a 6.65 kilowatt power. So multiplied by 100 EV chargers, that means if they all charge at the same time, the peak power capacity will be around 665 kilowatts. So for a building size like at this scale, their existing infrastructure is only 1.2 megawatts. So that means if we want to install EV chargers, 100 EV chargers like this, we'll need to upsize the transformer and also upsize the panel. And this is going to be a very disruptive and time-consuming construction work. So the lead time, so the construction time can be over 12 months or even longer. And considering the lead time of the transformer and the equipment, we're looking at 2 years or even more for the retrofit. And the average cost will be around $10,000 to $60,000 for each charger. And this cost will need to be paid upfront by the developer and indirectly paid upfront by the condo owner. So that's not really a reasonable way to install EV chargers at these locations. And in addition to the cost, there's also extra GHG emissions, from the construction work, and also if we push the power demand high, 600 kilowatt more, and also increase the capacity of the power grid generation, which means we need more generation from the grid, and that can be from the backup power, which is gas-based, more emissions, or even coal-based, that means more emissions as well. So that's what we mean that indirectly the car transfer the emissions to the building just because because of the requirements for EV charging. And this is not just a problem for for condos, apartments. It's a common problem for all the large car parks, for example, at corporate campuses or academic campuses. So one example, so why we're doing a pet project with U of A is that U of A is like the Windsor car park and the Stadium car park. Each car park has over 1,000 parking spots, and their existing infrastructure can only support 30 EV chargers at each car park. But for a campus scale like U of A, assuming there's only like 5% of people need to charge on campus, they will need on average 100 EV chargers or even more, 200 EV chargers at each of their car parks. So that's not going to happen if they use this traditional charging solution just to install chargers and let them charge freely. So what we do is we start from a basic calculation, like what's the actual charging power needed for the for the cars. So you found that, based on the average driving range per day by a Canadian, which is 50 kilometer, we see that we don't really need that high power. The reason is that, even at the worst case, the car to cover 50 kilometer range, at the worst case, we only need 15 kilowatt hour energy. And that's a very, worst case scenario where, which is a very large car, like a Ford truck in driving every day in -30-degree winter. And yeah, so the actual case to cover 50 kilometer range, the energy needed is only about like a 7 to 8 normally. And for condos where people live, they will generally stay there for over 10 hours. So we see that the actual power we need is only 150 kilowatt capacity, and for 100 chargers, and that's on average 1.5 kilowatts for each vehicle. And so that means somehow we need to, and basically all the buildings can support that 150 kilowatt power. So that means we need to control the EV chargers to make sure they won't charge at a very high power. So that's what we do, is we have a cloud-based load management system. We use that to control the EV chargers from the cloud, and we have a learning-based algorithms. We just use the cloud service. We use so the cloud service, so control will learn the behavior of the chargers and some historic information as well, and then use that to control the EV chargers. And on the front end of our software, we provide just a general monitoring service, where the operator, like the UFA parking service, they can see what's going on in the charging station, how many chargers are being used, how many chargers are idle, if there's a faulty charger, and what's the power, what's the revenue collected from each charger. But on the back end, what the software really does is the control. So with the control, we can install 4 to 12 times more EV chargers without any infrastructure upgrades. So again, for the UFA's Windsor car park,
SPG safety protocol, let's see, are they? No.
sorry.
Sorry, we had somebody unmuted. I'll check and make sure they're muted. Sorry, go ahead, Zhongyi.
Yeah, no worries. Yeah. So we can install 4 to 12 times more EV chargers on the same infrastructure without having to upgrade the infrastructure. Just to say, for the UFA's case, right now they can only support 30 chargers at one car park, but with the control, they will be able to install at least 120 chargers, or even 300 chargers in the same car park without having to access their own transformer. And that means it could mean like over $1 million cost saving for them. And also, because it's a cloud service, it's very easy to use. It can manage chargers. It can manage unlimited number of chargers. No on-site server, nothing else. And chargers don't have to be on the same circuit, which means they can be just on different levels, at different panels, because we can control the power of each individual chargers. So for clear, just an example is that for example, if this input supply is only like a 32 amp, so what do we do if there's 6 chargers right now? So what we do is just to split power, and for for cars that need more power, based on our historical information forecast, we will supply a higher current for this car, and for other cars that need less power, or less energy, we supply a lower amp current for them, and then we can suspend the charging of the rest of the cars, because right now with the level 2 chargers today on the market or in industry, the standard is that the minimum charging current is 6 amp, So below 6 amp, the car will just stop charging. So so that's why we need to suspend the charging of some other cars. So the cars that need that only minimum energy. And once the first car receives a fair amount of energy, we can suspend charging of the first car and then focus on charging of the rest of the cars. So we're doing testing right now at the UFA using real cars. We just don't have a whole lot of data right now to show, but once we have more data to show, we can have another presentation to show, more study results. But for general case, this is our case study for office building based on their behavior, like their driving cars behavior, is that overall we can reduce the infrastructure requirements by over 6 times. So without control, they will need 152 kilowatts available power to power these 19 EV chargers. But with our control, we can just limit the power to 25, and at the same time, we can deliver the same amount of energy to the cars and to meet all the requirements. And all of that because we have this learning and forecast-based algorithm, so that we prioritize down the cars with need more energy, and then just focus on those cars, and then we also prioritize on the cars that will leave early. And then for the rest of the cars, we can just give them a lower power, less energy, and so overall, the power will be minimized, but the energy delivery will still be satisfied. Yeah, so that's all of my presentation. So right now we haven't really got a lot of data, so we won't be able to show lots of them. But once we have enough data, we'll definitely show them with serious members.
Fantastic.
With
Thanks so
that,
much, Zhongyi.